Okay. Yesterday we had discussion regarding algorithms and introduction to algorithms. And this is the module 2. Yesterday we started. And of course, we understood in the C program, in the past module, we discussed about C program. And in this particular module, we talk about algorithms. There are multiple solution algorithms for any problem. So, in order to understand the best algorithm, in order to find the best algorithm, we make use of asymptotic notations. Asymptotic notations. So, that is used to check the performance of the algorithm. Based on that, you can decide which one is good, which one is bad. And we have taken one example how exactly algorithm will work, step by step working of problem solution is what algorithm is all about. And algorithm always works with the problem and a set of input with the set of output. And of course, we discussed algorithm solves the problem one at a time. Of course, there are multiple algorithms solving the same. So then you have to choose which one is better, which one is good. And these are the characteristics, 7 characteristics of an algorithm. Yesterday we understood. And how algorithm can be represented. Algorithm can be represented in 2 forms. One is using flowchart, another one using pseudocode. So while using pseudocode, there are 10 different uh, conventions that you have to follow. This is very important. In the examination also, they'll ask this 10 conventions. And of course, you need to answer this. So whenever you write if a statement should have end if. So that is the first, convention. And the same way, if you are using for statement should have end for. Same. This is while writing the algorithm. I'm talking. It is not related to program. And of course, so you can represent arrays with index numbers. So a few examples we discussed regarding algorithms. And today, as in the syllabus, the second topic we are going to start. So the second topic is nothing but finding the efficiency of an algorithm. So getting the efficiency of an algorithm is what we are supposed to discuss. So whenever we refer the term efficiency in the context of algorithms, so what happens? It always points to uh, two aspects. One is with respect to how quick it can run, how fast or how quick it can run, and how much memory it is going to take. So time and the memory, we call it as a time complexity and space complexity. So time and space complexity are to be analyzed in order to check the efficiency of an algorithm. And of course, the function that derives the running time of an algorithm and its memory requirement for a given set of inputs is referred as algorithm complexity. So among complexities, the first one, which you call it as the time complexity. So look at here, time complexity. Time complexity is the measure of running time of an algorithm for a given set of inputs. Running time, how much time it takes to run. So it is running time of an algorithm. It's a running time of an algorithm is what we talk about. So running time of an algorithm is what we talk about. And the space complexity also. Space complexity is nothing but how much memory space it is going to occupy. How much memory space it is going to occupy is what space complexity, and is the measure of amount of memory space required by an algorithm for its complete execution for a given set of inputs. So this is what you should understand. This is what you should understand about the complexity of the algorithms. So there are two complexities. One is time complexity, another one is space complexity. So time complexity is about running time. Space complexity is the how much how much memory is required by the algorithm in order to complete execution. Next point is about time complexity. Time complexity is typically measured by counting the number of primitive or elementary steps performed by the algorithm for its complete execution. So you should note very well. So how much how much time is totally depends on how many primitive statements that you have. Primitive statements means the elementary steps, very, very important steps. How many elementary steps it is having. So based on that, the time is going to be calculated. And these steps are mission independent. And of course, so if you write more lines of code in the program, what happens? It will take more time to execute. So it's very, very important that you should have very less, you should have very less elementary steps so that the algorithm will perform faster and better. And of course, these steps, these elementary steps are mission independent, and their count is directly depends upon the size, dependent on the size of input data set. Input is also very important in order to check the complexity, time complexity of an algorithm. If you give only 5 numbers or 5 input, so your program will run obviously faster. Instead, you give 5,000 numbers for calculation of average. So definitely it will take more time. So even input also plays a very important role in the efficiency of algorithm. And to represent and express the time complexity, we use a notation. We call it as asymptotic notations. So asymptotic notations are nothing but these are the notations, symbolical notations that are mainly used to express the time complexity and space complexity. Of course, space complexity it is not considered much because, of course, space you can buy, you can get, you add more memory, RAM chips. Okay, that's not a problem. Problem is solved. But time you will not get. Time is a very important thing that you will not get. So time complexity is more focused, more important than your uh, space complexity. So that is what you should understand. And of course, asymptotic notations. These are the notations I have told earlier also. These are the notations that are used for finding the time complexity. Of course, running time complexity. Look at the first point. Asymptotic notation is the most simple and easiest way of describing the running time of an algorithm. Running time, how much time it will take. So that is been explained here. And of course, it represents the efficiency and performance of the algorithm in a systematic and meaningful manner. So it is very, very important. So in the examination, they ask this question: what is asymptotic notation? Asymptotic notations are special notations that are used to measure the performance and efficiency of algorithm in a systematic and meaningful manner. So that is what you have to tell. And asymptotic notations are three. There are three common measures. One is the first asymptotic notation is the best case. Best case is nothing but fastest possible way. Fastest possible way representation is what you call it as best case. Suppose I'll give you one example. If you are searching a number, if you are searching a number out of 1,000 numbers, the first number what you choose, if it is the number that you are looking for, that is a best case. Out of 1,000 books in the library, you are looking for a book and you keep your hand on the first book. If that is the book that you are looking for, oh, that is the best time, best case. Second is worst case. You keep on searching. Last book what you take, 1,000th book, the last book, that will be the book that you are searching. That means you have searched almost 1,000 times. Whereas in the best case, you have searched only the one time. So that is the best case. Sometimes what happens, you take average case. So you take average case. Average case is nothing but, it's the average time taken by 3 or 4 times you make searches. Okay, so that is average case. So best case, worst case, and average case. Of course, you can also experience many times. So whenever you're writing an exam, you'll say, this is the best exam that I write. Next, you'll say, the average exam was average. That means not too good, not too bad. The third one is worst case. You have never done this exam so far like this. That is the worst case. So that is slowest possible, fastest possible, and average case is the average time. And of course, these terms we represent using big O notation, big omega notation, and big theta notation. Big theta notation is your average case. Big omega notation is your worst case, and big O is your best case. Is your best case. Is your best case. So this is what you should understand. So there are three notations, and these three notations are quite important. These three notations are quite important to understand. So that is what uh, asymptotic notations talk about. Further, we talk about big O notation. As I already said, big O notation always talk about the best case, upper bound. So big O notation is a method that is used to express the upper bound of running time, in the algorithm. If you run this algorithm on 20 different cases, and out of 20 different cases, one case will be the best performed case. So best performed case is always notated by O, big O. So it is denoted by big O. Using this notation, we can compute the maximum possible amount of time that the algorithm will take for completion. So that is the thing that you should understand. Of course, when you define mathematically this particular big O notation, consider f of n and g of n are to be two positive functions of n. So n is the number of input of data, and if f of n is big O of g of n, if and only if there exists a positive constant c and an integer n0 such that f of n should be less than or equal to c of g of n, where c is a constant, and all the inputs whatever you take should be more than n0. N0 means the first input, it should be more than the input should be more than one input. That is, n should be greater than n0. Okay, and the same thing you can write it like this. So the complexity of a particular function of algorithm, you can write it like this: big O of g of n. So I told very clearly, big O notation is nothing but it is the upper bound, the best case. Same thing it is being expressed in this particular graph. Look at here. So you are always taking the graph, you're always taking the graph of various computation functions, maybe f of n and g of n. And if c of g of n is the highest, then you write it like this. So the complexity, big O complexity, big O is nothing but best case. The best case complexity, big O complexity, is nothing but the best case. Best case uh, best case is all about the upper bound of the performance. Suppose if whatever the numbers you have, if the algorithm gives you uh, order of 1, that is a big O of 1, then the algorithm is a constant. If O of n, so where n is the number of inputs, the order or the best case depends upon the number of inputs n. So then it is a linear. If it is in a n square, it's a quadratic. If it is n cube, it is cubic. If it is 2 raised to power of n, then you write it as exponential. Of course, the complexity may be log of n, which is nothing but it's a logarithmic. So you can certainly represent based on the graph like this, the big O notation. Big O always talks about the best case. Next, working examples. In the examination, they give like this an equation. Derive big O notation if f of n is equal to 8n plus 7 and g of n is equal to n. So for this, you have to write the solution like this. To show f of n is O of g of n, we must consider positive constant c and integer n0 such that f of n should be less than or equal to c of g of n for all n greater than n. So the n0. This is what the definition is about. You write the definition. Next, you take 8 f of n is nothing but, in this equation, 8n plus 7. 8n plus 7 should be this. Should be less than c of n. Cn for all n greater than n0. Let us consider c is equal to 15, some number you take. If c is 15, that means 8n plus c should be less than or equal to cn, that is 15. So in this case, Now we must show that 8n plus 7 is less than or equal to 15n. And for this, if you specify n value as 1, so what happens? Uh, 8 plus 7. First, if you specify n value as 0, so what happens? 7, 8n is 0, 8n is 0, 7 is less than 15n, which is not true. So then you take n is equal to 1. In case of n is equal to 1, 15 is equal to 15. So, of course, this is true. This is true. So, therefore, you can certainly write it when n is equal to, there is n0 is the sample value. If it is 1, then this particular equation works. This particular equation works. This is how you can derive. The second example, of course, these examples I have taken from the textbook. Derive big O notation if f of n is equal to 2n plus 2 and if g of n is equal to n square. And of course, you have to write it in the same fashion. So f of n is equal to 2n plus 2 and your g of n is equal to n square. So if n is equal to 1, so what happens? 2 plus 1, 2 into 1 plus 2, it is 4. So 1 square is nothing but 1. So 4 is less than 1 is false. That is f of n is greater than g of n. So which is not that you are not supposed to prove that. Now you take n is equal to 2. Now for n is equal to 2, you just take. Now f of n is equal to 2 of 2, that is 6, 4 plus 2, 6, and g of n is equal to 2 square. So that is 4. So in this case also f of n is greater than g of n. So this is also we have to omit it. This is for n is equal to 1 also we have to remove it. N is equal to 2 also it is not working. Now n is equal to 3 you take, and if n is equal to 3, it is 2 into 3, 6 plus 2, 8, and n cube, that is 3 cube, 3 square is 9. So 9, which is what it is satisfying. It is what it is satisfying. Therefore, you can write the expression that is f of n is less than c of g of n, which is true for if n is equal to 2. So you have to derive like this. So n is equal to 3, sorry, if n is equal to greater than 3, greater than 2, that is correct. Or if n is greater than or equal to 3, you can certainly write like this also. So this is how you have to derive the big O notation. Big O notation for particular operation. And omega notation, as you know, omega notation is the least, that is lower bond, worst case. It talks about worst case. So the omega notation is a method used to express the lower bound of the running time of the algorithm, and the omega notation is denoted by omega. Using this notation, you can compute the minimum amount of time that an algorithm will take to completion. So that is what you talk about. And you can define this as, consider if f of n and g of n are to be two positive functions of n. So where n is the input size, and then f of n is omega of g of n if and only if there exists a positive constant c and integer n 0 such that f of n should be greater than or equal to g of n. So in the previous case, it should be less than or equal to g of n. But here it is greater than or equal to c g of n for all n is greater than n0. So mathematically you can hence f of n is equal to omega of g of n. So it is always talking about the lower bound. So you can see the lower bound you take c of n where it is meeting the c of n. So this is n0 we are taking. So graphical representation you can certainly have like this. And examples deduce the omega notation if n is equal to n square 2n square plus 4, where g of n is equal to 6. So in this case f of n should be uh, greater than c g of n, and of course we'll consider this case by specifying what we call it as uh, if n is equal to 0. If n is equal to 0, what happens? And if 0 means f of n is equal to 4. So 2 into 0 plus 4, it's 4. G of n 6 into 0 is 0. So in this case, f of n is greater. Okay, it can be considered. But you are supposed to take the lower bound, and that is if f of n is greater than g of n. So now you take n is equal to 1. So in this case, uh, 2 plus 4, 6 and 6. Now it is equal. So f of n is equal to g of n. Now you take n is equal to 2. So when you take n is equal to 2, f of n is 12 and g of n is also 12. So in this case also both are equal. Now you take n is equal to 3. So when you do n is equal to 3, f of n is uh, 22 and g of n is 18. So in this case, f of n is greater than g of n. F of n is greater than g of n. So obviously, this will be considered. Therefore, we can say uh, f of n is greater than c g of n if only if n is greater than 2. So n is greater than 2, or you can certainly write n is if n is greater than or equal to 3. You can also write like this. So this is one way of deducing the omega notation. Next, we have another example. Deduce omega notation if function f of n is equal to 2n plus 6 and g of n is equal to 2n. So in this case, first you take n is equal to 0. So if it is 0, 6 and 0, of course, f of n is greater than g of n. If n is equal to 1, so it is 8 and this is 2. And of course, this is second time also you get f of n is greater than g of n. So we can certainly, therefore, we can certainly say your function f of n is greater than c g of n for all n is n greater than or equal to 1. So you can certainly write this way. The third notation is a theta notation, which is neither the upper bound nor the lower bound, but it is in between. And, and the theta notation is a method that is used to express the running time of an algorithm between lower bound and upper bounds. And theta notation is denoted by the symbol theta. Using this notation, we can compute the average time that an algorithm will take for completion. So by definition, you can certainly write like this. Consider if you are considering f of n and g of n are two positive functions of n, where n is the number of input data, and f of n is the theta of g of n if and if only if there exist two positive constants C1 and C2 such that C1 of G of n is less than or equal to f of n, that is less than or equal to C2 G of n. So you have to consider lower bound, you have to consider the upper bound, in between you have to consider. So then you should call it as f of n is equal to theta of G of n. Like this, you have to just write it. So here is the graph that is representing the theta notation. So this is the upper bound C2 G of n, C1 G of n is the lower bound, and in between the function that you are having, it should be in between. So it is just this way you can certainly calculate the theta notation. And here also you will have a question, deduce theta notation of the function f of n is equal to 2n plus 8, of course. So you can say 2n plus 8, which should be greater than 5n. In this case, you can see where n is greater than or equal to 2. In this case, what happens? 2 plus 2, that is 8. 2 plus 2, 2 plus 2, 4. 4 plus 8 is 12, which is greater than 5 into 2, 10. So you can certainly consider this 2n greater, n is greater than or equal to 2. And of course, if 2n plus 8, which is greater than 6n, if you consider where n is greater than 8, in this case also, it is working fine. And if you write f of n, that is equal to 2n plus 8, which is less than 7n. So you cannot have 7n. So beyond 7n, it cannot do when n is equal to 2. So certainly you can certainly write 2n plus 8, which will be always greater than for 5 of n, and for 7n, it is less than. So this will be a lower bound and this will be a upper bound. So your C1 is equal to 5 and your C2 is equal to 7. So you have to calculate C1 and C2 in such a way that the constants after their inclusion in the expression, that should satisfy the lesser than and greater than. So lesser than the greater than the lower bound and lesser than the upper bound. So if you find C is equal to this one, then you can certainly write f of n is equal to 2n plus 8, that is equal to theta of 8, theta of n. So you can write like this. So this is theta notation. So normally, whatever it is given in the textbook, if you study, that is sufficient to understand. And some of the problems that are given in the exercise, you can certainly study those exercise. It is done. So that's all for today's class. In tomorrow's class, I'm going to discuss about introduction to data structures, the next topic in this particular module. Introduction to data structures we'll discuss. So thank you for taking your time to attend my class. Kindly enter your USN in the chat box for the sake of attendance, and in case if you have any doubts, you can contact me. And all the class recordings and notes, everything is available. Study material, everything is available in this particular website. Thank you. Have a wonderful day. Stay safe. So kindly enter your USN if you are not entered the US